presentations. We're going to move directly to the next one. Quantum Initiatives at University of Texas at Austin. We also have two speakers. Elaine Lee is one of them. She's a leading experimental physicist whose work advances our understanding of quantum dynamics and condensed matter systems. She's the Welch Foundation Chair in Science and Professor of Physics at the University of Texas at Austin, where she also serves as a co-director of the Texas Quantum Institute. She received her PhD in physics from the University of Michigan. Her work has been recognized by some of the most prestigious awards in science and engineering, including a Presidential Early Career Award for Scientists and Engineers, Sloan Research Fellowship, and NSF Career Award, and Thomas Peter O'Donnell Award, which in Texas know very well. She's a fellow of the American Association for the Advancement of Science and the American Physical Society. Her research really pushes frontiers of quantum physics and also lays the groundwork for transformative technologies. She has shaped collaborations, connect fundamental science to real-world applications to ensure advances in quantum physics contribute broadly to the technological innovation and societal benefits. And then we have a second speaker, and I guess we're going to divide it up again down here. Xiaoling Li. She's an internationally recognized leader in semiconductor materials and nanotechnology. She holds the Temple Foundation Endowed Professorship number 3 in the Department of Electrical and Computer Engineering at the University of Texas at Austin, and as an affiliate appointment in chemistry as the fellow of the Dow Professorship. She earned her bachelor's degree from Peking University and her PhD from the University of California, Los Angeles. She was a postdoc at Caltech and also at the University of Illinois, and also worked in industry in a company that was formerly called EpiWorks. She began her academic career at the University of Illinois Urbana-Champaign in 2007 and joined UT Austin in 2021. Her outstanding contributions have also been rewarded with a number of recognitions, including the NSF Career Award, DARPA Young Faculty Award, and the ONR Young Investigator Award. She's a fellow of IEEE, American Physical Society, and AAAS, and the National Academy of Inventors. And so she bridged semiconductor science with device innovation and really shaping the future of microelectronics and translating discovery into societal benefits. And with this, I'm going to hand it over to the first speaker.
Thank you very much. So just a personal note, I started my graduate career building solid-state quantum gates. And then I thought the problem is way too hard. I cannot, bet my entire academic career on that. But now that's a really exciting time to come back and revisit the problem in this field. And then I spent my postdoc 3 years at Gila, Colorado, working in a lab across the hall from Junyi. And their lab is so annoyed about noise, they went ahead and unplugged a lot of vending machines in the building because that was impacting their measurement. So I had to live without soda, but that's okay. A lot of things we're willing to do for science. And so I'm very grateful to the organizer, to Olga and the Texas A&M organizing this great event. I'm just gonna introduce what we've been doing in Texas Quantum Institute, a young institute compared to the A&M effort. I'm gonna tell you a lot of it, some examples of what we want to do. In fact, the hope is that some of you from company or government agency brought your checkbook. You can make it payable to Texas Quantum Institute. Okay, so we look at our quantum portfolio at UT Austin and decided our core strength lies in these 4 pillars: quantum algorithm, quantum material, quantum metrology, and system. So I'll give you a few examples of what we're working on, hoping to work on in each of these categories. So we have a group of young faculty that are very celebrated in the field of quantum algorithm, led by Scott Ayerson. And UT has made this a strategic area and hired quite a few young faculties. And the goal, of course, there is to understand computational power of quantum mechanics and discover applications where quantum computer can outperform the best classical algorithms. For example, quantum supremacy is a term that coined by Scott Ayerson. And this afternoon, you'll learn some new development in this field in a talk led by Nick Hunter-Jones. And in particular, I'd like to highlight a proposal that was just submitted through the Murray program, a Texas Center program led by a cosmologist a theorist in my department, contributed by Nick Hunter-Jones with theorists at Texas A&M. What they're trying to do is to take a very advanced concept like holography, developing cosmology, and use it for quantum information processing. And there will be some experimentalists and theorists coming from Gila, Colorado, joining that team as well. And hopefully, they would get to work on these exciting ideas together. And another thing, one of the things we heard from Google is that their approach is to take superconductor qubits and make quantum computer out of them. So the approach that has not been perhaps well represented so far is the approach using topological quantum computation. That's in line with the approach that Microsoft is taking. Everybody have talked about how critical it is to build a quantum computer that's fault tolerant. Topological quantum computing is designed to do that. So you will also heard from Junyi's talk, the particles the physicists talk about can either be a boson or a fermion. In the technological terminology, they're described by the spin of the particle. If they're half spin, they're fermion. If they have integer spin, they're boson. So these two particles are the fundamental building blocks of the microscopic world. But you can actually create what's called a fractional charge quasi-particle. By that, we don't actually take a knife and cut up the electron. In fact, you need to get them to work collectively. When you get microscopic particles to work collectively, they can have fractional charges. And these particles that we describe as anion, they're not fermion nor boson, but collectively, they can actually form states that can be interfere and braided together and create a new type of qubit. So these are very much at the frontier of condensed matter physics, but these are the approach taken by Microsoft to do superconducting qubits. So given there's industry leaders like Google, IBM, already making leaps and bounds in superconductor quantum computer, what scientific community, academic can contribute? Our thinking is we can either build new type of qubits based on anions and topological materials. This slide, I should say, is contributed by Leo Lee, a young faculty we recruited from Brown University. And another way that academic can contribute to this superconductor-driven quantum computer is to think about the scalability problem. Again, that's a problem that Junyi have discussed extensively. So how are people building supercomputing-based superconductor today? So these qubits need to be run at the extremely low temperature, for example, millikelvins. For fundamental reason, you cannot actually shrink the qubits down. They're on the size about a few microns. So what's a few microns? Human hair, a sheet of paper, is about 100 micron thick. These qubits are already very small, a couple microns. But semiconductor technology, of course, is already on the level of few nanometer. You cannot take that approach to shrink down the superconductor qubit down to a few nanometer. If you do that, you would really jeopardize the performance of these superconducting qubits. As a result, you can only fit so many qubits in a single dilution fridge. And the picture here by IBM is these big fridges that are housing about 1,000 qubits already. How do you further scale up? And you also heard from Misha that for really impactful quantum computers, you want to get to 10 to the 10th qubit. So the leading academics and companies are taking an approach to really build this gigantic cryogenic chamber for microwave cables and all of that. And they're already on the scale of 30 meters, and they're super expensive. We cannot just keep them build things bigger. Even in Texas, we cannot afford to do that approach. So the way to build a bigger and more useful quantum computer is to actually link them together. So taking the lesson from classical computer, can we link quantum computer processing units with optical fiber? And that's the approach that we want to take on at Texas, at UT Austin. We just submitted an NSF proposal exactly to tackle this problem. In our view, there are a lot of hard work to be done on material science, and those material science engineering method could allow us to network the computings together, make a 3 orders of improvement. And then we can take on designing clever devices, and finally using new protocols. These three methods combined together would allow us to make a quantum leap from what's called the quantum transduction problem from the current value of 0.1 qubits per second to 1 million qubits per second. So quantum transduction problem essentially take a qubit created in one platform and convert it to qubit in a different platform. This particular program is designed to take a superconducting qubits and convert the information to photonic qubits. And there's other form of quantum transduction to be worked out in cold atom, in other tri-bion system. Again, you need to figure out a way to write quantum information from one physical system to a different kind. So this is a type of a problem that we want to work on, is work on the quantum transduction problem. So I should mention that a lot of these programs are really championed by the young faculty at UT Austin. And Cheyenne Shankai is an expert in superconducting circuits. Lin Fan is an expert in quantum transduction devices. And Matteo Ippoliti is an expert in quantum algorithm. And also think about system value, system level analysis. What do you need to do to really realize that quantum advantage? Another type of quantum computer, smaller scale analog quantum computer, is called a quantum simulator. You have heard Richard Feynman's name being mentioned a couple of times already in today's event. And he wrote this very short article, 2 to 3 pages. Everybody should read it, where he asked a lot of really inspiring questions. So one of the questions he asked is, what could we do with layer structure with just the right layer? And in fact, today, we're at the golden opportunity to explore this and answer this question. So in the world of quantum material, people have figured out how to isolate a single atomically thin layers material or single unit cell thick materials. These are what's called the van der Waals material. It turns out you can find any building block from these van der Waals material. And the advantage is that you can actually stack them in any way that you want. So one of the things that physicists are learning how to do is to create these, what's called the Moiré superlattice. They're a type of a quantum simulator with a unit cell or a supercell on the order of a 10 nanometer. And it's an ideal lens to bridge the real crystal, real material, and the cold atom simulator that we've been listening about. So the cold atom systems has a unit cell essentially on a few hundred nanometers, and real material has a unit cell on the order of 0.1 nanometer. And these type of quantum simulator based on van der Waals material bridge that gap and would allow us to simulate different kind of problems. And there also can be built they can also build to create an array of quantum emitters. And as we heard, when you build these things bigger, there is a quantum advantage by allowing them to behave collectively. So at UT, we're fortunate to have a NSF-funded material science and engineering center. MERSEC, we have a team of more than 10 faculty working precisely on that problem. And I won't read out everybody's name. And just to highlight, Alan McDonald is an intellectual leader in a lot of these research globally. His idea has seeded a lot of the creative and truly groundbreaking discovery in the last 10, 15 years. So I think it should be stated clearly that quantum computer is not designed to replace classical computers. And today's supercomputer, and UT is proud to house some of the best supercomputer in the academic setting, and that's housed in the Texas Advanced Computing Center, and one of the NSF-funded leadership class computing facility that really includes the newest NVIDIA chip to do AI at scale. And even today, supercomputer, a lot of time, about 50% of the computing time is actually devoted to discover new material and to simulate chemical process, to design fertilizers and help agriculture industries, and also to discover new drugs. So what supercomputer are already doing, quantum computer is probably not likely to replace them anytime soon. So we still should support these large computing efforts. And at UT, this is also being used effectively to support material discovery. And we're lucky to have MERSAC director at U who's going to present at this event later today as well. So Texas is home to a lot of celebrated aerospace industries. And we actually, there's a few years ago, the state legislation also provided generous support for the aerospace industry. And UT, in the category of quantum sensing, has a new institute funded by NASA, and their goal is to put atomic sensor into space. So their goal is to use a quantum advantage of the measurement of mass change from space at unprecedented precision and resolution. And that institute is led by Professor Srinivas Bhattacharya. So he hopefully will be able to join us today. Again, this is a national collaboration involving people at CU Boulder, at UC Santa Barbara, and Caltech. One more thing we believe that the academic can contribute is to contribute new metrology tools. The idea is to invent new tools to measure the invisible currently. What I want to highlight a couple particular tools. One of them is co-invented by my colleague Ke-Ji Lai. And not only it can be used to study very fundamental quantum Hall phenomena that could be based, lay the foundation for topological quantum computing, it's already been applied to measure things like quantum transaction devices. And some of the image on the right shows how his group has measured acoustic waves in silicon vacancies in diamond, how they have been able to offer the ultimate sensitivity to measure some MEMS devices. And another tool that we heard from Texas A&M colleagues is you can actually using quantum coherence to do imaging and to do microscopy. Here's another example of how we can use sophisticated ultrafast spectroscopy to actually measure defect, and these individual defects can perturb semiconductor chip performance. And we are happy to share that we were able to successfully apply for some funding. Hopefully the governor's office signing checks to provide some instrument support for us to make these metrology tool accessible to the rest of the Texas Institute and industry users. So with that, I'd like to I've given you some examples in quantum algorithm, quantum material, quantum metrology. I want to hand it over to my colleague Xiuling Li to talk about how do we build these things at scale.
All right, continue the infrastructure beyond the metrology, and when we make devices, we need a clean room. And this is the UT Austin's Microelectronics Research Center, where I serve as the director. We have a 12,000 square feet, over 100 major tools, and very recently, we just got a $27 million upgrade for the clean room tools, so we are going to have a whole new array of tools enable fabrication at all levels. And we grow materials, including many kinds of different quantum materials, starting from a atomic level to control at the atom level with epitaxy, including 3, 5 compound semiconductors, 2D materials, oxides. So we start, we want to call it the small foundry. Hopefully with more funding, we'll develop into a bigger foundry that can supply especially lower TRL type of materials, not only to UT Austin, and hopefully the whole Texas, even beyond that. That is one of the bottlenecks for people to make devices. Is where do you get your materials, and especially when that material is not mature enough to get from an industry foundry. And the other aspect of this is, and we do fabrication. Once we get the materials, we do fabrication. The level of fabrications we do goes from atomic layer all the way to heterogeneously integrated architectures. And the middle chart over here is a chart from the DARPA HAPPY program. It literally compared what electronics is doing today versus what photonics is doing today. Electronics has been integrating on-chip, in-package photonics to this day is in play. You got lasers, detectors, modulators, everything in plane. So how do we take that through a 3D structure, a waveguide that's 500 micron long on chip? So those are some of the challenges, and we believe we're founded on that program, so we believe we have some ways to contribute to that one. And talking about integration, we are the home for the Texas Institute for Electronics. That's where the DARPA NGMM program is actually being performed right here. And we have 2 different facilities. The facility actually shared with the Microelectronics Center on J.J. Pickle campus is the 8-inch fab facility, and at the airport is the 12-inch facility. Just to add a few more slides on our young faculty who are contributing to different modalities of the quantum platform. And this is the superconducting qubit platform. And we have acoustics to help integrate different kind of qubits. And the Lin Renfen's research connects a hybrid quantum system from photonics, atoms, superconducting photonic acoustics, to make the scalability of different kind of quantum platforms possible, and hopefully taking it from millikelvin to room temperature also. And that's how we build devices. Before I end, I want to introduce this program. This is a newly founded program from NSF. Actually, we just started it September 1st. It's a $3 million program for 5 years to train students. This is at the graduate student level. We have a name for this program. It's QCAT, Quantum Cross-Platform Advanced Training for Future Innovators. And this is a comprehensive program where everybody has to do research, and that's the outer circle here. It's the immersive type of research, and we'll develop a quantum certificate and include professional development. If you want to be a professor, how we encourage you to do that, how we train to do that. If you want to start a company, hopefully the Texas ecosystem will be really helpful to actually spin off companies from this. And we're really excited about this program. In terms of the research approach, again, it's a hybrid. We wanted to train people to be ready for whatever comes next in the quantum technology. So we require students in this program called the NRT Fellow to actually cross different platforms or vertically cross different approaches. That means they need to have at least 2 advisors to have a dissertation topic that is cross platforms laterally or vertically. And want to use this platform to really call for partnerships between our university, other universities, and government and industry here. The immediate partnership we are looking for is for the NRT training program. We already have all these companies, IBM, NVIDIA, HRL, and the national labs who provided supporting letters for our proposal. And now that we won, we're really looking forward to this partnership. At the same time, we're looking for matching fund because NSF's money will not be able to cover everybody. And we want to have a broader impact, and we hope you join us to shape the future of the quantum workforce. And in parallel, we're establishing an industry affiliate program. And this industry, of course, includes government labs. Also, the value proposition is clear. You get to sit at the same table with all the other companies, and you get to easy access to innovation. We'll work out the IP agreement. And collaborative opportunities. And if you want your existing workforce to actually have some upscaling, we're open to that also. So with that, I look forward to welcome you to these programs and finding collaborative opportunities. And to end, so what we think this Texas Quantum Bill could shape the research landscape and how universities could contribute. These are some of the bullet points that we put down here. can we have a quantum analog of a CPRIT program, which is the cancer research program? Can we create some quantum advanced research programs that really gonna help society advance the humanity? And the Quantum Innovation Center, what kind of space that we can get to actually spark and stimulate small quantum startups? So those are the questions that we look forward to discuss with everybody. And ultimately, these are the things we really looking forward to have this quantum bill inspire us, push us, and put us together to answer and solve these problems. Thank you.